The aerospace industry is constantly pushing towards improved engine designs which meet the environmental norms and at the same time provide proper fuel efficiency. Engine simulations have now become an integral part of this design process, primarily because experimentally testing full-scale engines costs millions of dollars. However, in order to effectively simulate these large-scale engines, it is important to understand some of the physics underlying these multiple different processes that are going on when you look at turbulent combustion. Turbulent premix combustion, which forms the backbone of the gas turbine industry, is made up of multiple different interactions and processes. Some of them being flame-flame interaction, flame-turbulence interactions, and finally, turbulence chemistry interactions. Now, the latter one, turbulence chemistry interactions, is a fairly new addition in understanding what's going on and has been facilitated due to these improved computing facilities which are available to us, which allows us to really include multiple species and reactions which are more true to the combustion process. Now, my thesis has focused primarily on understanding turbulence chemistry interactions. And like I said, since it's a new field of research, there's just so much more that needs to be done or that can be done. Some of the key findings in my thesis have been using direct numerical simulations, which give you this beautiful three-dimensional picture of the turbulent flame. And at the same time, they've been compared with laminar flames as well, since we use a lot of laminar flame information in order to understand the chemistry of turbulent flames. And the first understanding that we've gathered from this whole analysis is the fact that chemical pathways, which basically tell you how the fuel gets oxidized into its products, doesn't really change too much from a turbulent flame to a laminar flame, and really laminar flames can give you a good idea of what's going on. However, you start looking at significant deviations when you zoom into the problem and you start looking at the flame structure. Now, the flame structure itself is a strong function of different factors. Stretch has already been identified as one of the factors. However, this thesis provides another important player in this whole picture, which is diffusivity, which comes in as soon as you introduce turbulence into the picture, and with increasing turbulence, the diffusivity also goes up, and has been shown to form a significant factor in determining the flame structure and its changes with turbulence. In the next 10 to 20 years, it's going to become quintessential to really introduce these diffusivity effects into laminar flames so that we can truly replicate what's going on in these turbulent flames and what's happening with respect to its chemistry. There is so much of interesting things which are happening around just specifically in turbulent combustion and turbulent chemistry interactions. I invite you to read my thesis and gain insight into what's going on and what's out there in this field. Thank you.